In the last video, I defined the Laplace transform and gave some examples. In this video, I want to talk about the first properties of the transform. Some of these properties are essential for the use of the transform to solve differential equations, which is our goal after all this setup. The first and most important, the Laplace transform is linear. This means that in a sum of various functions, I can do the transforms individually and then add up the results. Without this, the transform would be almost unusable, but this makes it very reasonable, particularly for linear differential equations, where the various pieces are indeed added up. The second property is something you might have noticed from the previous video. All of the outputs of the Laplace transforms were decaying functions. This is indeed a general rule. All functions in the S-domain are functions which eventually decay to zero. This is not a particularly useful property for solving, but it is a very valuable check for your own work. If you ever get a function in the S-domain which is not a decay function, which doesn't have a limit of 0 as s goes to infinity, then you have made a mistake somewhere in your work. There are a couple of small exceptions to this, which you'll see, but for the most part this will hold. Since the transform is linear, and since the functions that come out of it decay, there's a nice interpretation here for students who have linear algebra. Functions can form vector spaces. The Laplace transform changes some functions to other functions and does so in a linear way. Therefore, the Laplace transform is a linear transformation between vector spaces. Well, between which vector spaces? Well, the starting functions need to have a domain of 0 to infinity and need to be functions of some exponential order. So let me write EOF, exponential order functions, of the domain 0 infinity for this vector space. So functions that satisfy that condition. The output is a set of decaying functions on some domain a to infinity for a positive number a. So let me write this df plus, decaying functions, and plus indicating some domain of positive numbers. The Laplace transform is then a linear transformation between these two vector spaces. The next set of properties are all going to be very important for the mechanics of solving a differential equation. They involve multiplications by exponentials and domain shifts. Here's the first property. If I have a function and multiply by an exponential in the t-domain, the result is almost the same function in the s-domain, just shifted by a, where a is the exponential growth or decay coefficient that I multiplied by. The argument is given here in terms of the exponential definition of the transform. For the most part, the Laplace transform is not particularly symmetric. What happens in the t-domain is often pretty different from what happens in the s-domain. However, the case for shifts and exponentials turns out to be one of the few important symmetries in the system. However, to state the other side of this, I need another definition. A unit step function is a discontinuous function which starts at 0 and at some point jumps up to 1. The notation here is u sub a of t, where the jump occurs at t equals a. Step functions can be multiplied by other functions, and to do so is to basically remove all of the function f before the point t equals a, and then the function can continue normally after t equals a. If I do this with a shift, ua of t times f of t minus a, then the result is to remove the negative half of the function and shift it all over so that the positive half of the function now starts at t equals a. Why do I care about unit step functions and shifts? Well, let me first take the transform of a unit step function. I've already shown in the previous video that the Laplace transforms of discontinuous functions can give interesting results, even continuous functions themselves. And the same is true for the unit step function. Here's the calculation using the integral definition of the transform. The result is again surprising. The transform of a step function is exponential decay. In the previous video, there weren't any exponential functions in the s-domain. All the results were rational functions and powers of s. Only when I start with a strange discontinuous function do I get an exponential in the s-domain. And there's even more here. Say I have a step function multiplied by a shifted function f of t minus a. Here is the integral calculation for its transform. It involves the substitution of v equals t minus a, and the result is the Laplace transform of the original function, which I'll write f of s, multiplied by an exponential decay. And this is the symmetry here. An exponential in the t domain leads to a shift in the s domain, but a shift in the t domain, adjusted by a step function, leads to an exponential in the s domain. Exponentials turn into shifts in both directions. Again, this may be pretty strange and arbitrary for the moment, but I ask you to stick with me for this development. All of these properties will be needed in the final result when we put it all together to actually solve differential equations.